Hey everybody, Mr. Covey here, and today we're going to be talking about how to determine whether a polynomial is even or odd. So the kind of confusing thing about this is these words even or odd are words you actually already know. Like even and odd have a meaning in math already. Even numbers are 2, 4, 6, 8, 10. Odd numbers are 1, 2, 5, 7, 9. You guys know it. This is a different use of the same word. Okay, so when we call a polynomial even, there's a connection to the even numbers, but it's not exactly the same thing. I want you to think about it as a new vocab word. So when you see a polynomial and it's called even, what that's describing is a type of symmetry that the graph and the function have. And specifically with even functions, they have y-axis symmetry. And what this means is, if you look at the graph of the function, and I'm just going to draw a graph here. And you took your graph and you've reflected it over the y-axis. Please remember this one's the y-axis. It would match up with itself. So if you took this graph and you think about folding it, drawing it on a piece of paper and then folding it on that pink line, that blue chunk on the right side would match up perfectly with the blue chunk on the left side. And that's because this function I drew, this blue graph, is an even function. It has y-axis symmetry. Okay? So some functions have that y-axis symmetry, and we call those even functions. Other functions we call odd functions, and these also have a type of symmetry, but they have a what we call symmetry. Sorry. With respect to the origin. Pen's not working, sorry. Now this is kind of a confusing term, which is why I like to actually usually not think about it as symmetry with respect to the origin, because it's kind of confusing. And instead I think about it as having symmetry that's 180-degree rotational symmetry. And then in parentheses we can write about the origin or around the origin. And this blue way of thinking about it makes more sense. The idea is, if you have a graph, let's draw a quick little example here. If you have some graph where if you looked at the graph and you spun it around 180 degrees, so you flipped it upside down, you spun it around, it'd look exactly the same. So if you literally take your paper right now and you draw a graph like that, and you grab your paper and you flip it around 180 degrees, and then you look at it again, it'll look exactly the same. This red graph is an odd function. Okay, it has 180-degree rotational symmetry. If you rotate it 180 degrees, it looks exactly the same. Okay, that's the easiest way to think about what an odd function is. The way people describe that symmetry is it has symmetry with respect to the origin. Remember, the origin is this guy. So the reason they talk about that is because you're kind of spinning it around that pink dot. So that's why they say it's symmetry with respect to the origin. Cool. All right, let's look at a few graphs to make sure we kind of have this idea down. So you don't need to write this down. You can kind of just stick with me. Don't look at the equations on the left. Just look at the center for the graphs. And I'm going to pop them up. I want you to think about whether they're even. In other words, they have y-axis symmetry. Odd. They have 180-degree rotational symmetry. Or they don't have either of those types of symmetries. And keep in mind, like 99% of graphs don't have either of these types of symmetry. Okay, first one. Definitely even. Okay, so you look at the left side and the right side, you look at that y-axis right in the middle. If you flipped it over, that y-axis would match up. Next one. It's going to be an odd one. Okay, you rotate 180 degrees, it look exactly the same. This one's actually neither. So I know what you're thinking. You're like, oh, I could fold it over and match it up. But the key part here is even functions you have to be able to fold over the y-axis. The line of symmetry, we've talked about that in previous chapters, for this is not the y-axis, it's x equals -2. Okay, so that would be neither even nor odd. Even, definitely counts as even, cool. Odd, close your eyes, rotate it 180 degrees, open them, it'll look exactly the same. This one's actually neither. Be a little careful here again. Yeah, you could spin it upside down and it'd look the same, but the dot that you'd be spinning it around, the point that you'd be spinning it around, is not the origin. It's actually 0, 1. It's like that point right there. So just be careful if it is odd, that point that you'd spin it around to make it look exactly the same has to be the origin. That's why people say symmetry with respect to the origin. So this one would be neither even nor odd. Okay. Oops. Okay. Let's do these real quick. I think you guys got this idea. Once you pause, take 20 seconds to do 1 and 2, please. Okay, so if the function was even, it would look like that top thing there, because it'd have to have that y-axis symmetry. If it was odd, it'd look like that bottom thing. Okay. All right, so the real tricky part and the thing that we're going to focus on is how you determine whether a function is even, odd, or neither. The easiest way, not always the way that we're going to be able to do, is to look at the graph. And I don't think that's too bad. You guys will be able to get that down pretty quick if you don't already have that down. So graphically, you can sketch a graph, and if it has that y-axis symmetry, it's even. If it has that origin symmetry, it's odd. But there's other ways to check whether a function is even or odd without graphing it, particularly like if you didn't have a graphing calculator or something. And there's a way to do it numerically, and there's a way to do it algebraically. The algebraic way is really going to be our focus because we're an algebra class, and it's the trickiest way, but it's also the best way. Like it guarantees you the right result. In order to understand that numerical and algebraic way, I want to jump back to the previous page real quick, and I want to just think about actual points on these graphs. So if you look at this even function, what you might notice is, let's say this point right here was 2, was 2, 3, over 2 up 3. Because this function is an even function, you know another point that has to be on it. That's this whole symmetry idea. This has y-axis symmetry and 2, 3 is on it. What's another point that's on it? -2, 3. Okay. And this is true for any point over here matches up with a point over here. One way you could say this is if you know a point xy is on your even function, then -x, the opposite of x, will also give out the same y. Okay, this is a really important idea. If this first point is on the graph, then this second point is also on the graph, as long as it's an even function. Okay. If it's an odd function, a similar thing happens, but it's a little bit different. What happens is, let's say 2, 1 is on this graph, then -2, 1 isn't on this graph, but -2, -1 is. So if you know a point on an odd function, then you know another point on it that's the opposite of the x and the opposite of the y. If you want to write that fancy notation, which we should, if you know a point xy that's on an odd function, then you automatically know another point, which is -x, -y. This is an important idea. This is for an odd function. And this enables us to numerically check if a function's even or odd. Okay, because we want to see, for instance, if it's even, when you plug in 2, do you get out the same thing as when you plug in -2, or do you get out the opposite? And I'll show you an example in a second. Let's do that first. So 3x squared minus 5. grab your graphing calculator, type it in, hit the graph, that's what it looks like. Remember, if I'm ever going too fast for you, that's why we made this a video, so that you can stop and kind of go at your own pace. Okay. So that's what it looks like graphically. Well, I think you guys are picking up on this now. Oops, sorry. That graph looks like this. Definitely has y-axis symmetry, definitely looks like an even function graphically. Okay. Now, numerically, the way we're going to show this is we're going to do it with 2 and -2. So we're going to plug in 2 for x, and we're going to see what we get out for y. Okay, math, 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 we get out 7. We're going to plug in -2 for x. Math, 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 we also got out 7. Then we're going to pause now, and we're going to say, wait a second. If I plugged in 2 and I got out 7, I plugged in -2 and I got out 7, that's what happens when our function is an even function. Okay, so you kind of go back to what we were saying here. Oh, you mean like 2, 7, -2, 7 are both points? That looks like it's going to be an even function. Okay. Again, what we're doing here is we're looking at 3 different ways to try and determine that a function is even. So yeah, we already knew it by looking at the graph, but this numerical way is a different way to do it. The last way is algebraically, and this is super important. The reason this is really important is if you think about numerically, all we showed is that 2 and -2 give out the same y value, okay? Which makes me think that it's even, but watch this. Let's say 2 gives out 7, and -2 gives out 7. Yeah, this function kind of looks like it's even, but maybe it's not quite even. Maybe like it looks the same, but then it does something weird over here that it doesn't do over there. In other words, it almost perfectly matches up, but there's a little part that's messed up. Or it's messed up at like 1 point. Or maybe it looks similar like all the way out here, but then way out here they change a little bit. So in order to actually be able to tell if a function is even or odd numerically, you'd have to plug in 2 and -2 and 1 and -1 and 1.7 and -1.7 and 3.8 and -3. You'd have to plug in a million, bajillion, infinitely many numbers. So instead, we're going to use algebra, okay? And the idea is the same. You want to see that when you plug in x and when you plug in -x, you get out the same thing. That would be an even function, okay? Watch this carefully, please, and follow along. We're going to plug in x for x, which is kind of silly. You're like, what do you mean plug in x for x? It's just going to be the same. I get it. Let's just do it real quick, though. Okay, so we're going to take our equation, and we're just going to keep it how it is. We're going to replace the x with an x. We're going to get this. Now we're going to take our equation, and we're going to replace the x with a -x. Oops. Do these look exactly the same? No. But they're actually equivalent. And the way that you know that is by thinking about algebra that you know. So when you take a negative, an opposite of x, and you square it, what's -3 squared? 9. What's -12 squared? 144. Opposite of x squared is the same as x squared. The negative times a negative is a positive. So we can simplify this guy by saying the opposite of x squared is x squared, and that's true for any even exponent. And we end up getting this. Okay? And what you look at here is you go, oh, this is the same as this. In other words, when you plug in x for x, in other words, what you started with, and you plug in -x for x, they both end up giving you the same thing. When you plug in a positive and a negative, you get out the same y. You get out the same equation. That's telling you this function is even. Okay? These are 3 different ways to tell if a function is even or odd. The last way is going to be the most important. Okay, I'm going to run through 2 with you, and then I'm going to want you to do 3 and 4 on your own here. Okay, so again, let's toss this in our graphing calculator. Okay, you get a graph that looks like that. Graphically, this looks odd. Let's try and confirm that numerically. So let's plug in 2. 2 cubed minus 2, that's 6. So when you plug in 2, you get out 6. When you plug in negative 2, well, negative 2 cubed is negative 8. I'm sorry, I forgot to write the end, my bad. Negative 2 cubed minus negative 2. So negative 8 plus 2 is negative 6. So please be careful what our result here is. When we plugged in 2, we got out 6. When we plugged in negative 2, we got out negative 6. That's an odd function. Remember back to our picture here. When you plugged in 2, you got out 1. When you plugged in negative 2, you got out negative 1. So what we're doing here is you plugged in 2, we got out 6. We plugged in negative 2, we got out negative 6. That's an odd function. Okay. Algebraically, we got to be careful here. Okay. So we're going to see what we get when we just plug in x. Well, that's just the same thing. Okay. And now let's plug in negative x. Let's be careful here. So negative x cubed minus negative x. Let's simplify. A negative to a third power is still negative. You guys know that. Opposite of negative x is plus x. Okay. Here's the kind of tricky part. Look at the original. That's what happens when we plug in x. Here's what we got when we plugged in negative x. Clearly, those aren't exactly the same. But they are exactly opposite. The x cubed is a negative x cubed. The plus x is a negative x. They're exactly opposite of each other. That's what you want when you want it to be odd. They are exactly opposites of each other. Okay. All right. You could go ahead and try number 3. Pause the video, try number 3, and I'll toss up the answer here in a minute. Okay. So graphically, should have been able to graph this line. You guys know what this graph looks like. It's a line with a slope of 2 and a y-intercept of 1. And it has neither y-axis symmetry or 180-degree rotational symmetry because the point you'd spin it around isn't the origin. Okay, so it's neither even nor odd. Most functions don't have either of these types of symmetry. Numerically, we can confirm that. When you plug in 2, you get out 5. When you plug in negative 2, you get out negative 3. You don't get out the same thing. You don't get out the opposite thing. You just get out a random different number. This is not displaying any type of symmetry. Nothing's matching up. Lastly, algebraically, be careful. Again, this is the most important part. Here's what you get when you plug in x. You just get what you started with. When you plug in negative x, you get out this. I bet a lot of you guys said, oh, look, it's the opposite. It's odd. But it's not exactly the opposite. Yeah, the 2x changed to a negative 2x, but the 1 didn't change to a negative 1. In order for it to be odd, the thing you have to get out has to be like exactly opposite. Okay, so this one is neither even nor odd. Okay. We can skip number 4 for now. I want to focus on this algebraic technique. Okay, I'm going to do one with you, and then I'm going to want you to do the other 2. Okay, so again, graphically, you can determine whether functions are even or odd. You can do it numerically, but algebraically is going to be the winner. Okay, so the way to do this algebraically is to take your function and to plug in. Well, first of all, you can rewrite the function as it is. You can be like, hey, when I plug in x to my function, this is what I get out. I just get out the function. So this right here, the original, is what I'm going to be comparing to. Okay. Now I'm going to come down here, and I'm going to plug in negative x in the place of x. Okay, you got to make sure that you're relying on your strong algebra skills here. Okay, this is stuff you guys know. Okay, so I'm going to plug in negative x in the place of x. And just rely on your order of operations, your algebra 1 skills here. negative x cubed. Well, a negative cubed is still negative. So this is going to be negative 2x cubed. Negative 5 times negative x is plus 5x. So when you plug in negative x, you get out, oops, sorry. You get out this. Oops, sorry, I'm having some problems here. Okay. Your question here should be two things. Is this exactly the same as the red thing? If it was, the function would be even. Clearly, the red underlined thing and the blue thing are not exactly the same. Because they're not exactly the same, it's definitely not even. Even, it'd have to be exactly the same. You can jot that down if you want. Now, the second question is it odd? Is this and this, are they exact opposites of each other? Let's be careful. The 2x cubed became a negative 2x cubed, and the negative 5x became a plus 5x. Yeah, they're exact opposites of each other. Because they're exact opposites of each other, it is odd. Okay, so for odd, it has to be exactly opposite. So you would do this little algebraic test. Because it came out exactly opposite, you'd say it's an odd function, and that would be your answer. Okay, I want you to go ahead and try B and C. Pause the video, and then I'll show up the answers in a minute. Okay, so let's jump back to B first. So for B, kind of highlight here so you can follow along with what I'm saying. Here's the original function. Here's me plugging in negative x. I'm using my algebra knowledge. A negative to the fourth power becomes positive. So a negative x to the fourth becomes x to the fourth. A negative x squared becomes a positive x squared. If it's times negative 5, it's negative 5x squared. When I look what I get out here, it's exactly the same as what I started with. So it's an even function. Okay. For C, this one is a little tricky. I bet some of you guys got a little messed up here. I plugged in negative x. Sorry, here's what I started with. There's my original. I plugged in negative x. I said a negative x to the third. That's negative. Negative 2 cubed is negative 8. So a negative x cubed becomes the opposite of x cubed. So it becomes negative 2x cubed. It actually becomes negative. Negative x squared. Well, that becomes positive x squared. So it still has the negative 5. So it stays negative 5x squared. Plus negative x, that becomes minus x. Okay. Now be careful here. Here's the tricky part. Okay. Is this the exact same as this? Of course not. They don't look exactly the same. It's not even. But some of you guys thought it was odd. Let's be a little careful here. Yes, the 2x cubed became a negative 2x cubed. Yes, the negative 5x squared. Uh-oh. That's the part that messes it up. Okay. The plus x became a minus x. The 2x cubed became a negative 2x cubed. But the negative 5x squared, this guy right here, stayed negative 5x squared. So two of the terms became opposite, and one of them stayed the same. And whenever you have that mixing of some staying the same and some becoming opposite, it's neither even nor odd. Okay. All right. That concludes this video. Thanks, guys.